So welcome back to ECE 20002. One thing I would like to ask is, how is homework 4 going? So please type in chat, or speak up if you have feelings, Anyone think they're going to have trouble finishing? Almost done. Good to hear from you, Miles. Anyone else feelings on homework 4? We have one person requesting the deadline be moved. You're going to have trouble, says Diva. A lot of it left, should be able to finish. We're good. There's a lot of people missing. Use another day. All right. So I think I will go ahead, be generous, and say, hey, we'll move it back another day. So by my authority, I will say homework 4 is now due tomorrow, Tuesday, the 12th of July at 11:59 p.m. Eastern Time. So you heard it here first, folks. Homework 4 being moved back one day. One reason I do that is because grading has kind of really come to a crawl. I am upset that I don't have exam 1 completely graded yet. I need to really get on the case of some of the TAs. As for, we haven't even really started grading homework 3 yet, so I think another day is, fair. We're not done with our work. Might as well give you another time to do another work. Don't call me professor. I haven't earned that yet. How are they looking? Exam, I will tell you, so far with, I don't have the end value for the number of exams graded. You would think I would have that. Let me see what I got. So it looks like there are 90 that have been graded. So for the 90 graded so far, the mean is a 50.27. The median is a 50.3. And the mode is a 50. So all of those numbers basically line up. Perhaps the most important thing is distribution process. Homework 3, I'll try to get that done, a solution up soon. Again, we haven't even started grading it yet, so I've been trying to get on people's case about this exam. The most important thing is the standard deviation for the exam was a fairly narrow 15.34. So, the exam scores are fairly tightly clustered, which, that's usually a sign that the exam is, everyone's fairly equal in performance. The exam was fairly, equal in its, assignment of things, and, points are being assigned fairly. I have pretty good faith. So, right now, it looks like the mean after the curve is going to be a 79.78. It's less than 80 because some people turn in their exam after the grace period, so they are suffering a 10-point penalty. And let's see, the standard deviation after the curve is a 10.09. So it's supposed to be a 10. So everyone's grades are going to get very much lifted in a positive direction. Like, the curve amounts are insane. If you did really well, the curve is fairly minor, but I see someone got a curve of a 42. So pretty big curve. If you care more about the statistics, I'll present more about it later. Let me close out of that so I don't accidentally share it. All right. Let me go ahead, share my screen. So one thing I did on Brightspace is I put up to this week's weekly summary. So again, on the sidebar, weekly summaries, week 5 tells you the topics we're covering this week, the learning objectives tied to the course outcomes, and then the reading, lecture sets, and then a reminder of homework and the quiz. I didn't remind you about quiz 3 being due last Friday and Saturday, but like most of you remembered, so good job. I'll say it now so I don't forget. Quiz 4 is due, between Friday and Saturday this week. All right. Any administrative questions about the course? There ain't none. Let's go ahead and get back to our content. Are we still doing a LaTeX workshop? I don't know. Let me see if I have. It might be this weekend, might be next weekend. I'll see what we can do. Okay, so something weird is happening with the quiz 3 grades. I literally don't know why they won't show. If you didn't do it, I automatically assigned the 0 score. But like I can't get the actual scores. Like you should know what score you got, but like for some reason it's not showing up in the grade book. I'll have to investigate more. But like I spent a good, 15 minutes trying to get it to work, and it just will not show up. I might, worst comes to worst, I'll just manually enter everyone's score. It seems to update yesterday. I can check real fast. I got to close out grades. Oh, it did update. Huh. Yeah. Okay. Yeah, everyone's quiz 3 should be up. Pretty happy with quiz 3. With like one exception, everyone got a 3 or I guess a couple exceptions. Everyone got a 3 or a 2. Lots of 3s. Siraj, don't be late. Okay, but I'll tell you. The mean, median, and mode were basically all of 50 for the exam. They're not completely graded yet, but like yeah, the mean is like a 50.27, median's like a 50.1, and the mode is a 50. So standard deviation is like a 14.8. So that's really tight for a class this big. So that tells me something was there's may not have been an easy exam, but at least it was pretty fairly structured and everyone's at a similar performance level. So the curve will be slightly less than 80. After the curve, yeah, mean will be slightly less than 80, and the standard deviation will be slightly more than 10. So everyone's getting a huge shift up. A lot of people are getting shifted up like 30 points. So. All right. Yeah, I wish my time were saved. I need more of it in order to deal with all the grading. Yeah, like I said, I'll entreat you one more time, especially for homework 4. Please, please, please take your time. Make it look nice and neat, especially since I'm giving you an extra day. It just the amount of time we're spending on homework is quite large, just because we're trying to be very generous with partial credit. We're trying to be generous with, giving you points if your answer is consistent with a wrong answer. But that means we have to read all your work if you make a mistake. And that can really eat into a lot of time. And there's only, so many of us, and we have many other responsibilities like planning the next homework assignment, planning the next exam, so on and so forth. So please, please, please try to be neat with your homework. It'll save us time. If you don't get something, ask questions Piazza or on office hours so that, you get more points. Lecture set 5 on Brightspace. Will that be posted after class? Yeah, I'll post that today. Homework 2 been fixed yet. David, send me another email or something like that, or send it or email your grader and me. And if that hasn't been done yet, I'll make it right. That should be in the past. So if it hasn't been fixed for you, I'll fix it. I'll make sure it gets fixed at least. Oh, I guess the small administrative task. So good job for me because I managed to finish drafting all the lecture sets for this class. So all the lecture sets are planned out. I'm just trying to proofread them so that I minimize the number of typos. Me. I try. Typos still happen. Yeah. The last bit, I crammed a lot of information into lecture set 8. So if you wondered what the last lecture set is, it's number 8. Oh, you are generous with your praise. Not a professor. Still not a professor. Despite, maybe in your hearts, but definitely not in practice. Graduate lecturer. So I've evolved past GTA. I've been promoted past that. Yes. I'm procrastinating here, but yeah. So just so you know, it goes graduate teaching assistant, graduate teaching associate, and then graduate lecturer. Just like for your professors, it goes assistant professor, associate professor, and then a full professor. That's how it works. That's just how academic hierarchy goes. I won't answer that last question, Riyadh. A little too personal to share with the whole class. If you wonder, I'll tell you in office hours or in an email. All right, back to sharing the screen. We've procrastinated enough. So, transfer functions. This is kind of where we left off. So, as you recall, we talked about the different bases of signals. We went for the complex exponential basis, so we can do one-sided Laplace transforms. Went through the definition. Went through all the properties of Laplace transforms. So we built up a nice Laplace transform table. Then we talked about the inverse Laplace transform, where we do partial fraction expansion to get into forms that are in our table. Normally you have denominator polynomial of a greater degree than your numerator polynomial, so we know how to inverse Laplace transform those. And after we did that, we talked about impedance and admittance. So we introduced some circuits into the mix where we're, skipping the ODE completely and just solving it based off of transforming the circuit into the Laplace domain. Then we finished up talking about initial conditions, where we can represent, capacitors and inductors with initial conditions as their respective impedances or admittances in series or parallel with a voltage source or current source, respectively. Whew. How to watch what I was saying there. But now we're kind of past the circuit mindset. We're going to do a little bit more of the engineering mindset. So how do we get meaningful analysis and interpretation out of things? So let's go ahead and talk about the transfer function. So recall output of an LTI system at rest is y of t is equal to x of t convolved with h of t. So the impulse response h of t is the derivative of the complete step response. That's how we normally get it, because you normally can't apply a delta function in practice and see what the circuit output would be. By the convolution property, we get a multiplicative form of the output of the LTI system in the complex frequency domain. Y of s is equal to x of s times h of s, because, by convolution property, convolution in time becomes multiplication in frequency. But we could just solve this with algebra for h of s. H of s is y of s over x of s, which tells us that the Laplace transform of our output over the Laplace transform of our input is our transfer function. And this will be the same regardless of, the output or input. This should, have a nice fixed form. We call it, transfer function instead of impulse response. So our impedance and admittance forms of our circuit will tell us what the transfer function is. So if we have knowledge of the transfer function, we can find the output of any system at rest to be computed for any given input. Just like if we had knowledge of the impulse response in the time domain, we could figure out the output to any input in time. The transfer function is going to abstract away the entire topology of the underlying circuit. And remember, by topology, I mean that all the choices of components, how they're connected to each other, and their values, that's what I mean by topology of a circuit. And we don't need to have, carry that, circuit diagram around anymore, as long as we have the transfer function. So as you'll see, we're not going to deal with, circuits. We don't need the circuit diagram after we get, a good transfer function, especially if one, has the input and output directly in it. So the transfer function itself is the Laplace transform of the at-rest response of the system to the unit impulse. That's the little equation at the top. And having either h of t or capital H of s is good enough to find the other, because we have the Laplace transform and inverse Laplace transform, and we have all the tables and such. So any question about what I mean by transfer function or how it relates to an impulse response? Hearing none. Let's go ahead and do an example. So we look back to the series RC circuit. Let's see if I can find where we did the series RC circuit. It looks like it started on slide 51. And then we got a voltage divider equation where we said Vc of s is equal to Zc over Zr plus Zc Vn of s. And, it was at rest. So if we jump back to slide 69, we'll get Vc of s divided by Vn of s is what we'll call h sub v of s. It is a voltage transfer function. It relates two voltages. So depending on your choice of output, you obviously have a different transfer function. So if instead we wanted IC of s, it would be a, admittance type transfer function. But anyway, we'll get Zc of s over Zc of s plus Zr of s, which after we simplify, because this is 1 over Sc over 1 over Sc plus R, multiply through by S, and then we'll have to divide by R. We'll get 1 over Rc over S plus 1 over Rc. So it relates Vc of s to Vn of s. So find the capacitor voltage in response to Vn of t equals V times U of t. So as you can see, we no longer need to carry around our circuit diagram information. We have a transfer function. We have an input function. We have just a few steps we need to perform in order to figure out the output, because the output is, the numerator of our transfer function. So Laplace transform of our source. So a step function, with a nice scaling, becomes a 1 over s type thing. So Vn of s becomes V over s. So we'll multiply to get Vc of s. So Vc of s is equal to Hv of s times Vn of s. So 1 over Rc over s plus 1 over Rc times V over s. But look, we have, multiplication in our denominator and a constant in our numerator. Well, since we have a degree 2 polynomial in our denominator, we need to perform a partial fraction expansion. So Vc of s is equal to a1 of s plus a2 over s plus 1 over rc. We can go ahead and do our Heaviside cover-up method. So cover up the s in the denominator. And then what makes s equal to 0? Well, s equal to 0 itself. And then plug in s equals to 0, you'll get a1 equals v. Now you'll use my thumb, cover up s plus 1 over rc in the denominator. What makes s plus 1 over rc equal to 0 is s equals negative 1 over rc. So you'll get v times 1 over rc over negative 1 over rc. Therefore, a2 equals negative v. Perform the inverse Laplace transform. Vc of t is equal to v times quantity 1 minus e to the negative t over rc u of t. Yay! That's the answer we've always gotten for as many times as we've done the series RC circuit. Hopefully these common step responses and impulse responses are starting to stick in your head. It's good, it's good rule of thumb, practical type knowledge to have an idea of like the step responses circuits and the impulse responses circuits so that you can do this math a little bit faster. What questions do we have? Yes. Just mentioned, used cover-up method or Heaviside method, and that's how you got the coefficients quickly. So let's do the other thing. We'll have a series RC circuit with a transfer function h sub I of s is equal to IC of s over Vn of s. So this is an admittance type transfer function. 1 over ZC of s plus ZR of s. So 1 over RS over s plus 1 over RC after you do your simplifications. So it relates IC of s to Vn of s. Find the capacitor current response to that step function. So it's the exact same problem. We're just interested in a different output. So you'll also take the Laplace transform of the source, Vn of s, multiply to get IC of s. So HI of s times Vn of s is 1 over Rs over s plus 1 over Rc times V over s. But we can simplify. The s's cancel numerator and denominator. So we get IC of s is equal to V over R times 1 over s plus 1 over Rc. And you're like, wait a minute, that's already in something that we can look up in our Laplace transform table. It's a scalar multiple times, one of our Laplace transforms. This will become an exponential function. So inverse Laplace transform, IC of t equals V over R e to the negative 2 over Rc u of t. But even more, we can relate to Vc of t and IC of t. Because the current in the capacitor is equal to C times the derivative of the voltage. You could take the derivative of this. You'll get the derivative of a constant to 0. Derivative of V times negative e to the negative t over Rc is positive V over Rc times e to the negative t over Rc. We need to multiply by C. So we get exactly what we have here for IC of t. So good, that checks out. Furthermore, we will see that HI of s is just SC times HV of s. That one takes a little bit more to see, but multiply by SC in the numerator, you get 1 over R times S in the numerator. Why is that? Well, because we're messing with the numerator, the denominator stays the same. So we should get, HI of s is equal to by Laplace transforming the left side. If we Laplace transform the right side, we'll get S times C times HV of S. So the relationship between the outputs is known and expected, and the relationship between the transfer functions is also expected. Any questions about transfer functions? This is tied to a learning objective that you know how to use both convolution and transfer functions in order to solve problems. What do you mean by parallel? Nope, both are series circuits. We say, this is a series RC circuit. One is just saying the output is VC of S. One is saying the output is IC of S. So if we went back to slide, what slide did I say? I think I went past it. Let's go to slide 50. Slide 51. Instead of, it's the series RC circuit, but I'm asking for VCFT in the first example, then I'm asking for ICFT in the second example. But it's the same circuit. Definitely a series circuit. You're welcome, so on. Okay. So now on to our final topic of the lecture set, which is response decomposition. So this is, where we use to gain insight into how the circuit works. So there are many ways to decompose the complete response of an LTI system. So, once you say we have either VCFT or ICFT or, some other, voltage or current in a system, where we have, any number of resistors, inductors, capacitors, we can, or I guess, you can also throw in, ideal transformers, ideal op amps, and constant gain dependent sources. So, all the things that make it LTI or allow the system to stay LTI. It's faster or more insightful to look at one decomposition over another. So we've talked about forced and natural responses, but we'll review it a little bit here. And then we'll also talk about a zero input and a zero state response. And then we'll talk about the steady state and the transient responses. So when we talked about ODE methods, we talked about the forced response and the natural response. So the natural response was called our homogeneous solution. And it's all the terms associated with the roots of the characteristic equation. So it's going to have undefined coefficients in the absence of specific initial conditions. So, that's the key point is, these responses, exist for an ODE without initial conditions. We could still talk about a natural response and a forced response, and in the ODE that's not an IVP, initial value problem. So the counterpart is the forced response or particular solution is all the terms not associated with the natural response. So typically they are associated with your input, your forcing function. But, the most general term is all the terms not associated with the natural response. So we already know how to do this decomposition. We talked about it, several times in the lead up to exam 1. I don't think I need to belabor this point too hard. But now we'll have a new type of decomposition, the zero input and zero state response. So this is a new one. And this one only applies for specific initial conditions with a specific input. So you can't just talk about, oh, here's a circuit, what is the ZIR or ZSR? No, you have to talk about, here's a circuit, it starts at rest and the input is, a sinusoid, what is the ZIR and the ZSR? Then that's okay to talk about. So the zero input response, which I've been saying is the ZIR, is all the terms associated. I guess I should say is. Zero response, input response is. Just grammar right there. ZIR is all the terms associated with the specific set of initial conditions of a system when the input is set to 0. Hence the name zero input response. So basically, it's how does the circuit output, what terms are in the circuit output when just the initial conditions are there. The zero state response, or what I've been saying is the ZSR, is all the terms associated with a specific input to a system when all the initial conditions are set to 0. Hence, the state of the circuit is 0, so zero state response. So another way of saying that is the ZSR is all the terms that happen when we have just an input there and all the initial conditions are ignored. Here is, the caveat. The zero state response will differ from the forced response whenever the input corresponds to a root of the characteristic equation in the system. So if the input overlaps with a 0 of h of s. So we haven't encountered this too much yet, but the numerator of a transfer function could be factored into zeros. S minus 0, 1, S minus 0, 2, and so on up until S minus 0, M. And then if that happens, you'll get a case where you don't have the ZSR equal to the forced response, because you get 0 output when you would expect it otherwise. Questions? We'll do an example soon. Let's go into the example. So here is a parallel RC circuit. Hey, that's the one we talk about a little bit less often than the other ones. You can see we'd like to do the first order circuits for examples just because they go fairly fast, and they tell you the process without giving away the answers to more complicated second or third order circuits. So find Vc of t, the voltage across capacitor with capacitance C, in this circuit with resistance R. And the input is a step response IU of t, or not a step response. The input is a scaled step function I times U of t. And we're told that there's a non-zero initial condition on the capacitor. Well, the first thing we're going to do is take the Laplace transform of the whole circuit, so the source and the admittances with initial conditions. So we'll get I of S, or I over S, I should say, for our applied current source. We're using admittances, so we'll write the resistance as 1 over R. We'll say this admittance is SC, and the initial condition of the capacitor will work in opposition to the defined current into both the capacitor and the initial condition source, with the initial condition source being C times Vc 0 minus. Okay, so by superposition, we'll find a response to the 0 initial condition, hence the 0 input response first. So let's turn off our input. So when you turn off a independent DC current source, it becomes an open circuit. So by Ohm's law and equivalent admittance, so Vc of ZIR equals IC divided by YEQ. So we'll get CVC 0 minus times, well, the equivalent admittance here is going to be 1 over R plus SC. Just add them together. Hence, you'll get something that looks like this right here. We can simplify this. We don't like having fractions within fractions yet. So we'll multiply through by R just to get things into this form. Then we realize, well, as much as we don't like having fractions, we don't like having a non-zero coefficient in front of the highest term of our denominator, the highest power term of our denominator, I should say. So we'll simplify and we'll get Vz of ZIR is going to be Vc is 0 minus times 1 over S plus 1 over RC. Now what we're going to do is find the zero state response. So the response to the input alone. So we turn off this independent current source. When we do that, it becomes an open circuit. And we get that by Ohm's law and equivalent admittance, Vc as ZSR is going to be I in over YEQ. So we'll get I over S divided by all over, 1 over R plus SC. But we multiply through by R, and we get I over S times R over RC plus S plus 1, or RCS plus 1. I'm a little tongue-tied right now. But what you see on slide 75 is what I'm trying to say. Again, we don't like having our highest power of S have a non-unity coefficient. So we want to divide through by RC, and we'll get Vc ZSR is equal to I over C times quantity 1 over S times quantity S plus 1 over RC. Close quantity. So we'll go ahead and do our partial fractional expansion. So we'll get A1 over S plus A2 over S plus 1 over RC. Okay, say it with me. We're going to do Heaviside cover-up method. Use your thumb, cover up the S. That is 0 when S is equal to 0. So we'll get I over C times 1 over RC. So the C's cancel, and you're left with R times I. Then you'll take your thumb, cover up the S plus 1 over RC. What makes that equal to 0? Negative 1 over RC. Plug that in for S. So you'll get IC times 1 over negative 1 over RC. Again, C's cancel, and you're left with A2 is equal to negative R times I. So we'll inverse Laplace transform each component. So the zero input response was Vc0 minus e to the negative 1 over RCT U of t. And the zero state response was Ri times quantity 1 minus e to the negative 1 over RCT U of t. Adding them together, you get VCT is equal to Ri plus quantity Vc0 minus initial condition minus R times I, close quantity, times e to the negative 1 over RCT U of t. Because by superposition, you can just add the components together and get your final Vc of t. What questions do we have? Hearing no questions, I'll move on again. So, steady state and transient responses. So, the third decomposition we'll talk about today is decomposing the complete response based off of their behavior. So the functional form that each term of our response takes. So the steady state response is all terms that are constant or sinusoidal, i.e., as time goes into infinity, they stay bounded. The transient response includes all terms that are not in the steady state response, i.e., anything with exponential growth or decay involved. So you cannot find this for arbitrary inputs. This must be done post hoc, which is Latin for like after the fact. So like after you have written your response using the transfer function, then you decompose and say this is the steady state component, this is the transient component. You can't use it as a superposition style. I'm going to solve one part first and then the other. You don't know how to do that because you don't know how each thing is going to behave until after you find the solution, complete solution. So as a reminder, in ECE 20002, we are interested in both the steady state and the transient components of a response. If you just tell me the steady state response, you'll only get partial credit. Because we want to know how transients behave on all circuits. So that's all the decays like e to the negative 1 over RCT, e to the negative R over L times T, things like that. And you have the factors of 2 involved when you have RLC circuits. In ECE 20001, we focused only on steady state behavior with sinusoidal input specifically. So we called it the sinusoidal steady state, or SSS. So the best tool for solving circuits in SSS is phasors. So if you are interested in only steady state behavior and want to ignore the transient response, then just use phasors. So let's do a quick refresher on phasors. So this should be a refresher exercise. So find the steady state response of Vc of t using Laplace transforms, given that In of t is equal to I1 cosine of omega naught t u of t in the circuit starting at rest. So starting at rest and having a sinusoidal input, and we only want sinusoidal output, that's like 3 conditions right there. That means we can, use phasors in the circuit. So we're actually not going to do the phasors the first way. We're actually going to do it, the formal way using Laplace transforms and transfer functions. So let's do it the formal way, and then we'll do it the quick way. So we'll take the Laplace transform of the source and write admittances. So Laplace transform of the cosine is going to be I1 times S over S squared plus omega naught squared. We're writing admittances, so we'll get 1 over R and then SC starting at rest, so we don't need to include a parallel current source. And then, of course, we change all these lowercase letters into capital letters to denote Laplace transform for our signals, of course. So Ohm's law and equivalent admittance, so we'll say Vc of S is equal to In of S times YEQ. So In of S is going to be the I1S over S squared plus omega naught squared. And then our YEQ is going to be 1 over R plus SC in the denominator. But we can multiply through by R, and we'll get, this right here at the end of step 2. So we'll simplify our expression for Vc of S. So we don't like having, leading powers be different than 1. So we'll get I1 over C times S over S plus 1 over RC times S squared plus omega naught squared. By partial fractions, we have to do Vc of S is equal to A1 over S plus 1 over RC plus A2S plus A3 over S squared plus omega naught squared. Since we have this, affine form above s squared plus omega naught squared. We know we're going to have to, plug in special inputs, do things the formal way without coverlet method. So I'm just going to do the whole problem without coverlet method. And we'll multiply through by the denominators to clear the fractions. So we'll get IC of S, or I1 over C times S equals A1 times S squared plus omega naught squared plus A2S plus A3 times quantity S plus 1 over RC. So plug in negative 1 over RC. You'll get A1 equals I1 over RC squared times quantity 1 over RC squared plus omega naught squared. A2 is going to be pretty challenging. What did I choose? I chose S equals to 1, it looks like. So yeah, I get 1 over 1 plus 1 over RC. Mess. Plus more mess, which was, what we wrote up here. And then simplify more. This took me a few tries to do. It's algebra, but it's very easy to make a mistake. And eventually I got I1 over RC squared over 1 over RC squared plus omega naught squared, which was exactly the positive version of A1. But it took me a lot of tries to figure it out. And then finally, A3 is equal to I1 times omega naught squared over C times 1 over RC squared plus omega naught squared. That I got by plugging in S equals 0. So we'll perform the inverse Laplace transform after massaging the sign-like term. So here we're going to have, constant times this bit, e to the negative 1 over RCT, plus, well, this is a sine or cosine term with A2. So we'll get a very similar bit times cosine of omega naught t. And then lastly, we'll have to use one of these omega naughts for our sine function, and the other one will, stay off to the side. So we'll get omega naught over 1 over RC squared plus omega naught squared sine of omega naught t, all times u of t. Bit crazy when you do it this way. So let's use some trigonometric identities to combine the cosine and sine terms. So the steady state response isn't this transient part. This is the transient response, this first term, but the last two are steady state. So a times cosine of theta plus b times sine of theta is equal to square root of a squared plus b squared times cosine of theta plus the arctangent of negative b over a. So we'll get, VC steady state of t is equal to I1 over c times square root of 1 over RC squared plus omega naught squared times cosine of omega naught t minus arctan of RC times omega naught, all times u of t. Any questions about how we got here? Definitely a lot of algebra involved. You can see why, Laplace transform is powerful, but it doesn't spare you all the work. You still have to do a fair bit of work. Oh, I didn't know that ahead of time. Well, okay, that's not completely true. I did know ahead of time that it was going to be, equal but opposite A1 and A2 in this problem. But that's not because I could just, stare at it and figure that out. It's because I solved the circuit using ODE methods before, And I was like, oh, this is what I'm going to get. So I knew that it had to be equal and opposite by ODE methods, or Wolfram alpha if you prefer. Yeah, definitely use Wolfram alpha to check my work on this one. So here's our last example and our last thing we're going to do as part of lecture set 4, monumental occasion, because this was a pretty thorough lecture set. So sinusoidal steady state example. So find the steady state response of Vc of t using phasors, given In of t is equal to I1 cosine omega naught t u of t in the circuit starting at rest. So now, instead of using 7 steps, which were pretty complicated to find the steady state response, we'll do sinusoidal steady state in just 4 response, the fast way with phasors, just like we did in ECE 20001. So we'll write the phasor form of the source and phasor admittances. So we'll have I1 at an angle of 0, because, using the cosine reference, this is an angle of 0. Maybe you're not used to seeing the angle written as a complex exponential, or an imaginary exponential. But, remember, by Euler's identity, e to the j theta is equal to cosine theta plus j times sine of theta. So, having the angle be like that, we'll just write it as e to the j0 and always deal with the real part. The imaginary part just comes along for the ride. But we're not interested in it. So this phasor admittance is 1 over r. This phasor, susceptance is omega c. So now we can find Vc of s. Or I guess I should say, Vc of j omega. I'll put that down as a correction to make. Now, yes, isn't it kind of weird to write your argument as j omega? Well, yeah, it's kind of a weird thing, but it shows the relationship to the Laplace transform a lot easier if you do. So it's just think of it as a notational tradition rather than like, oh, I'm plugging j omega in places and how would I undo that? Like, yeah, just think, j omega in place here for notational tradition reasons. I guess I don't need the dot on this circuit, so get rid of the dot. So Ohm's law and equivalent admittance, Vc is equal to In over YEQ. So I1 e to the j0 over 1 over r plus j omega naught c, where omega naught is our specific frequency. I guess I should label that 2. So we'll simplify our expression for Vc. So, okay, right now we have the rectangular form of the denominator. If you remember ECE 20001, the best way to solve these things is, whenever you want to add and subtract, you use the rectangular form. When you want to divide, you switch to the polar form. So let's switch the denominator to the polar form. So we'll have I1 e to the j omega, or j0, all over square root of 1 over r squared plus omega naught squared c squared. Magnitude is just the sum of the squares of the real imaginary components, and then e to the j arctan rc over omega, or times omega naught, because it's opposite of b, or it's going to be b over 2a. So omega naught c divided by 1 over r is just rc times omega naught. But we can simplify this a little further. We'll have the magnitudes. When you divide phasors, the magnitudes divide and the angles subtract. So we'll get I1 over square root of 1 over r squared plus omega naught squared c squared e to the minus j arctan of rc omega naught. So going back to the time domain, we'll just take, we'll have to multiply through by e to the j omega naught t, and then we'll have to take the real part. So we'll get I1 over square root 1 over r squared plus omega naught squared c times cosine of omega naught t minus arctan of rc omega naught all times u of t. So I guess I should write, yeah, Vc of t is equal to Vc j omega times e to the j omega naught t, and then real part. To make that very clear. Same answer, benefit of less work, but you don't get that transient response component, which, you know, in ECE 20,002 we're very interested in, but in 20,001 you were able to answer a lot of questions without it. Now let's prove that these answers are the same. All we have to do is take the c, multiply through by the denominator. When c goes inside the square root, it becomes c squared, so we'll get 1 over r squared, and then c squared omega naught squared. Yep. And of course, the stuff inside the cosine is exactly the same. What question do we have about this? It's important to know for homework. I don't think we're going to have phasors on the exam. It's important to know how to use Laplace transforms convolution according to the learning objectives. What more questions do we have? Okay. Quick administrative note. I will have to cut office hours short at 1 p.m. because I have a doctor's appointment I need to get to. So if you are going to office hours today, please try to make the earlier part of it. I will be out of office hours by 1 p.m. Brightspace will show you your score after the curve. They were supposed to be released today. I need to get on some of the TA's cases to see when the rest of the exams will be graded. Some of the TAs are done, some are not. And homework 3 is not even started grading, so that's another problem. All right. Class dismissed. Bye, everyone. You're welcome. Goodbye. Bye-bye.